Perfect. Okay, so as I was saying, we have a homomorphism of real semisimple algebras, and suppose that we have a Cartan decomposition of G0. Okay, then we can extend this Cartan decomposition by F to a Cartan decomposition of H0. So more precisely, there is a Cartan decomposition of H0. So say H0 is equal to K prime plus P prime, such that F of K lies in K prime and F of P lies in P prime. Okay, so to prove it, we simply use the correspondence from the theorem above. So we first have to extend the situation to a situation between complex semisimple algebras. So we simply take the complexification of G0 and H0. Okay, so let G be the complexification of G0, H the complexification of H0, and F to be the complexification of the real homomorphism F. We will need to work with the real structures associated to G0 and H0, so just let me give them a name. So say that, let's call them sigma and sigma prime, for example. So let sigma and sigma prime denote the conjugation with respect to G0 and H0 respectively. So recall that Cartan decompositions came from Cartan involutions. So for example, the decomposition of G0 comes from a certain involution theta that commutes with sigma. So the Cartan decomposition of G0 comes from a certain involution. We can already say that it's an involution of G that restricts to G0, which essentially means that this involution theta and sigma commute. And also, being a Cartan involution meant that this composition gives a compact real structure on the complex semisimple algebra G. Okay, so now recall that we can extend tau to a certain compact real structure on H, and we can also extend theta to an involution of H that corresponds to H0. But the problem is that this new involution may not restrict to H0, so we have to go around this problem. And it will be essentially the same method that we used in the last session. So extend tau to a compact real structure tau prime on H. And then what we know is that there exists an involution corresponding to H0 so say that it's theta prime, such that theta extends to theta prime. And in fact, we can be more explicit about this, because if we revisit the proof, essentially we obtain that theta could be written in the following way. It could be written in the form theta prime equals beta sigma prime beta minus 1 tau prime, where beta was an inner automorphism that extended the identity. Beta is in the inner automorphism group of H, and the identity of G extends to beta. Okay? So obviously, theta prime commutes with tau prime. And this means that theta prime would restrict perfectly to the compact real form of H. But the problem is that we want an involution that commutes with sigma prime, so that it restricts to H0 instead of the compact real structure. And the easy way out of this is to simply take the conjugate of theta prime by beta minus 1. So in this case, take theta prime to be equal to beta minus 1, theta 1 prime, sorry. So this is a new involution. This would be beta minus 1, theta prime, beta. So this is again an involution. It corresponds to H0 because beta is inner. Corresponds to H0. And now we can check directly that theta 1 prime commutes with sigma prime, sorry. So we check that theta 1 prime, sigma prime is equal to sigma prime, theta 1 prime. Okay. So for example, let's compute the right-hand side. Sigma prime, theta 1 prime, by the definition of theta 1 prime, is equal to sigma prime, beta minus 1, theta prime beta. And now we use the explicit expression of theta prime. So this is equal to sigma prime, beta minus 1, theta, sigma prime, beta minus 1, tau prime, beta. And now note that this beta minus 1 cancels with this beta. And now the sigma prime cancels with sigma prime, so that the final result is beta minus 1, tau prime, beta. And now for the left-hand side, we have that theta 1 prime sigma prime is equal to beta minus 1, theta prime, beta, sigma prime. Now we substitute theta prime. So this is beta minus 1, beta, sigma prime, beta minus 1, tau prime, beta sigma prime. And this first beta minus 1 cancels out with the beta. And this gives us sigma prime, beta minus 1, tau prime beta, sigma prime. Okay, so if sigma prime and beta minus 1 tau beta commute, then we are done. But this is direct from the fact that theta prime does commute with tau. So let me write it just for clarity's sake. To note that theta prime tau prime is equal to tau prime theta prime, And by writing this out, it should follow. So this means that beta minus 1, no, sorry, beta sigma prime, beta minus 1, tau prime is equal to tau prime beta sigma prime beta minus 1 tau prime. I think this should work. Check. No, I think this is also the case. So I'm trying to see that beta minus 1 tau prime beta commutes with sigma prime. Now I don't remember how it went. I think I have it written. I guess we can save the situation. See if I have it here. Right. Mm. So this came from okay. So I think this should work. So in this case, start again from the fact that theta prime and tau prime commute. And let's write the definition of sigma 1 prime. Let's see if this works. Okay. Now I don't remember. Beta. So maybe it went directly. So sigma prime beta minus 1 tau prime beta. So this could be written. Let's see, we have theta prime is equal to beta sigma prime beta minus 1 tau prime. So we can, for example, recognize this beta minus 1 tau prime as the last factor here. This means that beta minus 1 tau prime is equal to sigma prime beta minus 1 beta prime. So now this is all equal to, let's see, sigma prime beta minus 1 beta prime with beta. So this is equal to beta minus 1 beta prime beta. Okay, on the other hand, if we write sigma prime, right, beta minus 1 tau prime beta sigma prime, now this is equal to and I can seem to remember how this went. So I'll just take note of this, and for the next session I will simply tell you, because the fact is that sigma prime and this conjugate do commute, and this comes from the fact that theta prime commutes with tau prime. And I know it follows directly by taking the adequate conjugate, but now I can seem to remember it. So let's simply say, assuming that sigma prime commutes with beta minus 1 tau prime beta, then we have directly that theta 1 sigma prime is equal to beta minus 1 tau prime beta. Okay. So I'll try to keep note of this, and maybe in the next session or when we upload the video, I'll give in the description the proof of why this is true. Okay, but for now, let's simply take this as a given. Okay. Well, at any rate, this means that sigma 1 prime and sigma prime and theta 1 prime commute, and thus sigma 1 prime does restrict to H0. Okay. So thus theta 1 prime restricts to H0, and also note that theta extends to theta prime and beta extends the identity, and this means that also theta extends to theta 1 prime. Okay, this is because beta extends the identity. Okay. And now this should follow, because if we take the Cartan decomposition associated to theta 1 prime, we see the following. So note that the decomposition H0 equals K prime associated with theta 1 prime is the desired Cartan decomposition. So why? Because if we have, so suppose that we have an element x in G0, then if x is in K or if x is in P, this means in each case that theta of x is equal to plus or minus x. Okay, so now take f of x. If f of x is in K, then this means that theta 1 prime of f of x is f of x. And if f of x is in P, then the same holds, but with a minus sign. But simply evaluate sigma 1, theta 1 prime f. Since theta 1 prime f extends theta, this means that this expression is also equal to f of theta x. And theta x is plus minus x. So in the end, this gives us plus minus f of x. Okay. So this means that f carries k to k and, sorry, k to k prime and p to p prime. So we're done. Okay. Assuming this part about that, I can't recall now how it went. So this is the algebraic version of the Kaplan-Leibniz-Mostov theorem. Sorry? Oh, yeah. So this is the algebraic version of the Kaplan-Leibniz-Mostov theorem. This was originally proved by Mostov, if I remember correctly. And there's also the geometric interpretation concerning symmetric spaces. So I'll just give a quick review of how these subalgebras, so how this theorem how this theorem explains certain geometric properties of symmetric spaces, and to be more precise, how it relates to totally geodesic submanifolds of a symmetric space. So this theorem is a geometric interpretation for symmetric spaces. So suppose that we have a symmetric space of non-compact type. Then this means that the symmetric space is written as G mod K, where G is a non-compact semi-simple D group, and K is a maximal compact subgroup. And we have geodesic symmetries at every point, and from this one can construct a Cartan decomposition of G associated that relates to the geometry of M at the coset corresponding to the identity. So we have an induced Cartan decomposition. And now let's consider as our homomorphism the inclusion of a semi-simple subalgebra of G. So in terms of Lie groups, then one would have a semi-simple subgroup of G. So let H be a semi-simple subgroup. And consider the inclusion of the corresponding list of algebra H to G. So here we are reversing the order with respect to the rest of the chapter. So now the homomorphism is from H to G. So the theorem that we just proved, the Mostov theorem, says that we can take a Cartan decomposition of H, and we can take a Cartan decomposition of G such that they are compatible with respect to the inclusion. In other words, recall that Cartan decompositions are conjugate by elements of the adjoint image of G. So what this means is that taking an adequate conjugate, we see that H is going to split with respect to G. So by taking an adequate G in G, what we see is that at G of H has a Cartan decomposition which comes from restricting the Cartan decomposition of G. So this is, I think I'm going to write it down here. At G of H is equal to at G of H intersect K plus at G of H intersect P. And this is precisely the Cartan decomposition of H. So in other words, what this means is that H is invariant under the Cartan involution of G for the adequate conjugate. So these are usually known as well-positioned or canonically embedded subalgebras of the Lie algebra G. And now this is going to relate to the totally geodesic submanifolds on M. So this is because there is a well-known correspondence between invariants of algebras, Lie triple systems, and totally geodesic submanifolds that pass through the origin. So recall that there are bijections between the following sets. So we have the set totally geodesic submanifolds, that pass through the origin. These are equivalent to Lie triple systems. Okay. So the subspaces of P that are closed under the triple bracket, and the theta invariant subalgebras of G. And the correspondence was given as follows. So for example, say that you start with a totally geodesic submanifold sigma, then the corresponding Lie triple system is the tangent space of sigma at the origin. Conversely, if you have a Lie triple system, say that it's called V, then from P one can construct a totally geodesic submanifold by using the Riemannian exponential map. And now we can also go in the other way. From a Lie triple system, we can construct a theta invariant subalgebra by taking the smallest subalgebra of G that contains V. And this is precisely V plus its first bracket with itself, where this left-hand side is in H and this right-hand side is in P. Okay. And to finish the correspondence, simply take any theta invariant subalgebra of G, so say that it's Q. Then one can construct a Lie triple system by taking the projection of Q on P, or equivalently the intersection of Q with P. So these maps given here are all bijections. And what we are saying here is that if you take a semisimple subgroup of the isometry group, then a conjugate of this isometry subgroup corresponds to a theta invariance of algebra. So the corresponding orbit to the origin is totally geodesic. So by the corollary, there is an element of G such that G minus 1, which is the subgroup corresponding to at G of H, then its corresponding orbit through the origin is totally geodesic. Or equivalently, one can write this as the image under the left multiplication by G of the orbit of H through the point G minus 1, O, which is now congruent to the orbit of H through G minus 1, O. Okay,
Can I ask a question?
Yes.
Are you sure that the map from the middle to the right is surjective?
It's surjective. If I recall correctly, yes, I think this is from submanifolds and holonomy, if I recall correctly.
No, but like, I mean, the left map is definitely bijective, but like the right map, I think you might have two different subalgebras, which are both theta stable, and their piece parts coincide, but the one has a larger K part than the other.
Maybe you have to assume that yeah, that may be right.
Because I think, for example, if you think of Rhn minus 1 inside Rhn, you can on the one hand you can just take the correspondingly triple V and consider the V bracket V plus V, and then that would give you this Rhn minus 1 as an orbit, and then all the other orbit will be of the same dimension. It will be like a foliation. But then you can also take a larger K part. You can take not just the bracket of V with itself, but the whole normalizer of V in K. And that would give you the same orbit through the base point, Rhn minus 1, but it will be a C1 action. So all the other orbits will be, oh, sorry, maybe you should be like Rhn minus 2 inside Rhn. So yeah, so then one thing would give you a C2 foliation, but then if you take the whole normalizer of V in K, that would give you a C1 action. So the other orbit will be of larger dimension. So these algebras are one inside the other properly.
Yeah, even though they have the same parts in P.
Yeah.
So what this would mean is,
So
what this means is really that, so we have these two maps, but they're not inverse to one another. Only one composition is the identity, I think.
Yes,
right?
yes.
Okay, yeah, you're right. You're right. So this, maybe it was too quick to say this. So really what you would have is that if you take the map from the middle to the right, and then you take the map from the right to the middle, then this composition is the identity. So if you start with
precisely.
V, you take this algebra generated by V, and then you take the projection, and now this is the identity. But this is not true conversely. So what you have is that if you start from something in the right, the result of the composition is a smaller subalgebra.
Yeah, so you can say something like minimal, or like, theta invariant subalgebras of G, something like minimal among those with the same P part, but that's, I guess, just clumsy. Yeah. Anyway.
Yeah, fair enough. No, yeah, but you're right. But yeah, this first is a bijection and the rest are not. Okay. At any rate, the only thing that I need is the fact that there exists a map from the right to the left.
Yeah.
From the right to the left. But yeah, thanks. Didn't catch that. Okay. So this gives that there is a point that's such that the orbit of H is totally geodesic. And this is the geometric version. So theorem. And it states that every semisimple subgroup of G has a totally geodesic orbit. Okay. In reality, these two theorems are equivalent, even though we just proved an implication. Okay. So this finishes the first part of the chapter in which we discussed simply the existence of extensions. And now we're going to cover a new part on S homomorphisms, which are going to be homomorphisms of complex Lie algebra that behave more or less like irreducible representations. And the idea is that we will have uniqueness properties for the extensions of real structures and compact real structures. Okay. So this next section is going to be called S homomorphisms. So the idea is to essentially generalize the notion of irreducible representation to arbitrary homomorphisms. And the idea will come from the following lemma. So, in which we will suppose that we have a representation of a complex Lie algebra. So let f from G to G of V be a representation complex Lie algebra. Where V is obviously a complex vector space. So then we have the following. First, if G is simply a complex Lie algebra and F is irreducible, then there is only one map. There is only one inner automorphism group. So I have to write something. So suppose that F is a representation, but taking values in a certain subalgebra of G of V. So suppose that F of G is contained in a certain subalgebra H. Okay. Now, if F is irreducible, then the only inner automorphism extending the identity on G is the identity of H. So we have the following proposition. If phi is an inner automorphism of H, and the identity map extends to phi, then phi is also the identity map. And now, in the case that G is semisimple, and our target subalgebra is either the whole GLV or simply SLV, then the converse holds. That means that F is irreducible if and only if the only inner automorphism extending the identity is the identity. And now note that this new property can be stated for general semisimple Lie algebras. So let's prove this. For the first part, suppose that we have such an inner automorphism phi, and suppose that it extends the identity. So the restriction of phi to F of G is the identity. Okay. Then since we are with matrix Lie groups, we can consider the subgroup associated to H, and we know that the inner automorphism group of the Lie algebra H is the adjoint image of the Lie group H. So if H is the connected subgroup corresponding to H, then we have that P is of the form at C for a certain C in the Lie group H. So if we prove that C is a scalar multiple of the identity, then we are done. Okay? But this is a consequence of Schur's lemma, because note that for any element of G, we have that at C of f of x is equal to f of x. And this means that C fx C minus 1 is equal to fx, or equivalently, that C commutes with fx. So essentially what this means is that C is equivariant with respect to the action of G on the vector space V. So now we can apply Schur's lemma to conclude that C is a scalar multiple of the identity. So C is lambda times the identity matrix for a certain lambda is a non-zero complex number. And this means that at C is the identity map on H. Because recall that it's taking the conjugate with respect to C. And now for the second part, suppose that G is semisimple. But now let's assume that F is reducible. And let's find a non-trivial element that extends the identity. Okay, so if the representation is reducible, then this means that we can write V as the sum of two invariant subspaces. So then V must be equal to V1 direct sum V2 for invariant subspaces. Okay. Then take, for example, A to be the identity map on V1 and to be minus the identity map on V2. This map is obviously an equivariant map with respect to the action of G. And what this means, by simply reversing the argument above, this means that the map phi to adjoint of A. Now this is an inner automorphism GLV, and it's obviously equivariant. Sorry, and it extends the identity because it's equivariant. Okay, so this gives a contradiction. And if we want to prove the same for H to be equal to SLV, we simply have to adjust this operator so that it has determinant 1. So in the case that H is equal to SOV, then simply choose C to be equal to the determinant of A minus 1 and change phi so that phi is now equal to at CA. Which now is an inner automorphism of SLV. So in both cases, we have found a non-trivial inner automorphism that extends the identity, and this proves the lemma. Okay, so far so good.
Yeah, it's all clear.
Okay, so we'll simply take this property and promote it to a definition. So this will be called an S-homomorphism for general semisimple D algebras. So definition, suppose that F is a homomorphism of complex Lie algebras. Then we will say that F is an S homomorphism if the only inner automorphism that extends the identity is also the identity. So we say that F is homomorphism if the only phi is an inner automorphism that extends the identity. Is also the identity.
Is the fact that it's inner important?
It's going to be important because recall that when we are constructing the extensions of our real structures and our involutions, we're always trying to take conjugates by inner automorphisms, because that's how we knew, that was the way that we used to construct to make this correspondence between involutions and anti-involutions. And in the proofs of the previous and in the previous session, the main effort of the proofs was to see that when we use this correspondence and we try to relate it to the homomorphism, then we could always choose the inner morphism so that it extends the identity. So the idea is that now most of these the intermediate homomorphisms that appeared in the proofs are going to be the identity map. That's the idea.
Yeah. Can there be an S homomorphism such that anyway there exists some automorphisms, not an inner one, that extends the identity?
So an automorphism that extends the identity,
but it's not inner.
But it's not inner.
So it's an S homomorphism, but there might be something not inner that extends it.
So I wouldn't say that it's not possible. I can think of an example. So so I think the easiest example would be to try to look in say, for example, in SLNC or SO2NC, wherever there are not too many non-inner automorphisms, right? So you have, for example, you either in the case of complex simple algebras, you have either 1, 2, or 6 cosets of int G inside the automorphism group.
Yeah, I guess like maybe you can start with some Lie algebra with some outer automorphisms. Then you can take some outer automorphism. You can look at its fixed point subalgebra.
Yes.
On the fixed point subalgebra, it will be the identity, obviously. And then you can just ask, is it possible for the fixed point subalgebra to be like semi-simple? And that would be, I guess, the answer.
That would work, for example, maybe. So what if, for example, we try any involution? If you try an involution and you restrict it to its fixed point set, maybe that can work or something of this sort.
Yeah, I think like there should be some on SLNC. There should be some when n is greater than 2.
Yeah, I think
there should be some outer automorphisms such that the fixed point set is still a semi-simple subalgebra. It's just not clear. It will be something like SO-NC or something. It's just not clear whether that embedding of the fixed point subalgebra into the original algebra, whether it will be an S homomorphism. So like, what if there will be actually some inner automorphisms that also extend the identity?
Yeah, it could be the case.
But yeah, I guess, yeah, I don't want to take your time with this question. I thought maybe just there was some counterexample like in the book.
No, in the book, it doesn't really have a counterexample, if I remember correctly. There is only one example covered by Onishik, but it's not really related.
Yeah.
Yeah, in the end, he basically gives an example of an S homomorphism that is reducible. In the case that we change the codomain, but about seeing if there are outer automorphisms that extend the identity, he doesn't bother with this because we only need it for the inner part.
Yeah. I guess it's not that important. Sorry.
Oh, no problem. Okay. So for now, let's see. The first consequence that we can see now is that recall that from the previous session that we can always extend inner automorphisms. So we call that if F is a homomorphism, well, an S homomorphism now, then suppose that we have, say that alpha is an inner automorphism of G, and suppose that we have two extensions of this alpha. So suppose that alpha extends to, say, alpha prime and alpha second. Okay. Then it's very simple to see that the identity map of G, since this is alpha minus 1 alpha, this has to extend to alpha prime minus 1 alpha second. So this means that alpha prime minus 1 alpha second is the identity, and alpha prime is equal to alpha second. So more generally, one could say that we have a well-defined extension map. Okay. So now let's try to relate this again with compact real structures and with general real forms and involutions. And we'll see that now this extension is going to be more rigid. Comes in the form of the following proposition. So suppose that F is an S homomorphism. And suppose that, let's start with compact real structures. So suppose that tau is a compact real structure in G. Then we knew that we can extend tau to a compact real structure on H, and in the setting of S homomorphism, there is only one way to extend tau. So there exists a unique compact real structure tau prime on H such that tau extends to tau prime, and now say that we have a real structure on G that extends to a real structure on H. So if sigma and sigma prime are real structures on G and H such that sigma extends to sigma prime and sigma commutes with tau, recall that in the general setting we couldn't assert that the extensions of sigma and tau commute, but in the case of S homomorphisms, this will be the case. So then sigma prime and tau prime commute, and as a direct consequence, these compositions, so let's call it theta prime, this extends theta, where theta is simply the composition of sigma and tau, which is an involution in this case. So for the proof, in the first part, we simply have to see the uniqueness. So now suppose that tau prime and tau second extend tau. And what we saw is that these two compact real structures must differ by an inner automorphism that extends the identity. So there exists an inner automorphism beta such that beta extends the identity and tau second is equal to beta tau prime beta minus 1. Okay, but if beta extends the identity, then it must be the identity. So beta is the identity in H, and thus tau second must be equal to tau prime. And for the second assertion, the idea is more or less the same. So in this case, let's construct, suppose that sigma prime and tau prime do not necessarily commute. Let's construct a conjugate of sigma prime that does commute with tau prime, and let's prove that in reality this conjugate is already equal to sigma prime. And we did it in the following way. So we took an automorphism which was sigma prime times tau prime squared, which is an automorphism that is positive definite with respect to the compact real structure tau prime, and gamma to be equal to phi to the minus 1/4, which is an inner automorphism of H. And we already know that the conjugate of sigma prime with respect to gamma, which we will call sigma 1 prime, so gamma sigma prime by gamma minus 1 commutes with tau prime, sorry. And we simply have to check that gamma is the identity. So for this, note that we can write the identity of G as sigma tau squared, okay? Because since sigma tau commute, sigma tau is an involution, so sigma tau squared is the identity. So this must extend to sigma prime tau prime squared, which is phi. Okay, so phi extends the identity, and recall that in the case that phi was a positive definite automorphism, then not only phi, but all powers of phi extend the identity. So in particular, the identity map must extend to gamma. Okay, but gamma is an S homomorphism. Sorry, but F is an S homomorphism, so gamma is the identity map. And this means that in reality, sigma 1 prime is equal to sigma, which means that sigma prime must commute with tau prime. The last part is obvious because because theta is simply the product of sigma with tau, and since sigma extends to sigma prime and tau extends to tau prime, then by definition of theta prime, theta must extend to theta prime. Okay. So for now, what we've proved really is that the extension of a compact real structure is unique. For the moment, we don't really know if the extension of, if we take a real form in G, which is not necessarily compact, and we extend it, if the extension is unique. Okay, but we will give more details on this right now. So for now, we know. So for now, we have proved that if F is an S-homomorphism, and U is a compact real form of G, then there exists a unique compact real form of H extending G. There is a unique compact real form, say W of H with f of U contained in W. Okay. So what about the rest? So for this, we will be introducing the notion of real forms that are of the same kind. And this will be related to the thinking diagram automorphisms that is induced. So, brief reminder, suppose that G is a complex semisimple algebra. And recall that if we take the quotient of the automorphism group of G, modulo the inner automorphism group of G, then this was exactly the automorphism group of the thinking diagram. And we will see that in reality, conjugate, in the case of involutive automorphisms, conjugate involutions are going to give the same thinking diagram automorphisms. So suppose that theta 1 and theta 2 are involutions corresponding to certain real forms. And suppose that they are conjugate. And phi is an inner automorphism such that theta 2 is equal to phi theta 1 phi minus 1. Then, if we consider the quotient, then the cosets determined by theta 1 and theta 2 are the same. This is because if we take theta 2 and its corresponding coset, this is equal to phi theta 1 phi minus 1 into G, or equivalently, this is equal to theta 1 phi theta 1 phi minus 1 into G. And notice that this element here is in the inner automorphism group of G, and this element here is a conjugate of an inner automorphism. And since the inner automorphism group is the identity component of the whole automorphism group, and conjugation preserves connected components, this is also in the inner automorphism group. Okay. So what this gives is that the coset of θ2 is also the coset of θ1. This process is not reversible. So, for example, think of any complex simple D algebra that has whose Dingin diagram has only the trivial automorphism. That doesn't mean that there is only one real form. Okay. So we just have one direction. Conjugate involutions give rise to the same Dingin diagram automorphism. Okay. So on the other hand, recall that we already know the automorphism groups for the complex simple D algebras. So we had that the quotient of all automorphisms mod inner automorphisms is equal to the automorphism group of the Dingin diagram. And in the simple case, this was equal to S3 if G is of type D4, which corresponded to SO8. It could be C2 in the case that G is either SLNC, SO2NC, or E6, or simply the trivial group in any other case. So from these observations, we're going to make the following definitions, and then we'll finish for today. So suppose that G0 is a real form of G. So we will say that G0 is of the first kind if its corresponding involution is simply an inner automorphism. Now, in the case that there are only two cosets for the inner automorphism group, so if the automorphism group of the Dingin diagram is C2, we say that any non-inner automorphism, any real form that is not of the first kind is of the second kind. So G0 is of the second kind. If it corresponds to an involution in the outer part. And more generally, if we have two real forms, we will say that they are of the same kind if they belong in the same coset of the inner automorphism group. In general, G0 and another real form G0 prime are of the same kind in their corresponding involutions. Are in the same coset of the inner automorphism group, or equivalently if they give the same linking diagram automorphism. So we'll stop for today, and the last thing that we'll do is to see that when we have a real form of G that extends to two real forms of the same kind, then these two real forms are going to be the same, which is sort of an extension of the uniqueness theorem for compact real structures. And that will essentially be the end of the chapter. We will see a small remark that states how the notion of subalgebra has come to be, and after that the chapter will be done. So this will be it for today.